Welcome back to Science Modernizers. Welcome back to this video. Today we are going to solve the Northwest Regional Mock Examination, the March 2024 session. We are going to be solving Physics Paper 2, and in this video we are going to call it part 1, where we are going to see the first 4 questions of the first section. Then in the next video we are going to see the next sections, including data analysis. So let's get started with the video. So let's get started with the very first question. Now the question reads: the force F on a current carrying wire is at right angles to a magnetic field given by the equation F is equal to BIL, where I is the current, L is the length of the wire, and B is the magnetic flux density. A says what is a homogeneous equation, and B says show that the above equation is homogeneous. So let's get started with the correction. Now, the very first thing we see is what is a homogeneous equation. So let's define that. A homogeneous equation is an equation in which the base units of all the additive terms in the equation are the same. That is, the base units or dimensions of the left-hand side of the equation to be equal to the base units or dimensions of the right-hand side of the equation. Now, for example, if we have the force F is equal to MA, the base unit of F should be equal to the base unit of MA. Now, force can be getting from has the unit of a Newton, and a Newton is simply a force which would cause a body of mass 1 kilogram to accelerate by 1 meter per second squared. So the unit of 1 Newton is equivalent to a kilogram meters per second squared, and here we see the mass, which is also measured in kilogram, acceleration, which is measured in meters per second squared. So we see that the units on both sides are the same. So that's the meaning of a homogeneous equation. Now we can't actually equate two quantities which are not having the same unit. For example, we cannot say force is equal to pressure. Impossible, because the unit of force is not equal to the unit of pressure. Okay, the next equation says show that the above equation is homogeneous. Now, to show that F is equal to BIL is homogeneous, it suffices to show that the unit of F should be equal to the unit of BIL, where B is the magnetic flux density. Now, the unit of F on the left-hand side, we can use Newton's second law, which from where we get F is equal to the mass times the acceleration of the body, that's F is equal to ma. Now, from here, we see that the unit of mass is simply equal to a kilogram, and the unit of acceleration is the meters per second squared. So from there we can deduce that the unit of F will simply be the kilogram meters per second squared, and that gives us the unit of the left hand side of the equation. Now let's get the unit of the right hand side of the equation. That's the unit of BIL. Now we have that the base unit of I, where I is the current, is simply the amperes. And to get the base unit of L will simply be the meter. And so for the base unit of B, we get that the base unit of B can be gotten from B equal to mu naught I divided by 2 pi r, which is the force per unit current length in a given magnetic field. That's a magnetic field, that's a magnetic flux density. And so what we get is we can now get the base value of the base unit of B, but mu naught becomes a disturbance, and we can use the relationship between the magnetic force between two current carrying conductors, which is given by mu naught I squared L divided by 2 pi r. Now I use I squared, assuming that the current flowing through both conductors have the same intensity. But if you use F is equal to mu naught I1, I2, L, all of that divided by 2 pi r, there is no problem, since the amperes will simplify and will still become the ampere square. And so from here, making mu naught the subject of the formula, we get mu naught to be 2 pi rf divided by r squared L. And so if we deduce the base units, that's by solving that and replacing the base units of r, f, l, I squared and L, we see that for I, the base units we cancel, so the units of F is a kilogram meters per second squared 2 pi is a dimensionless constant, and so that's going to be equal to, we have times R, which is the meters, divided by I squared, ampere squared, times the meter. So the meter will cancel, and I'll be left with force per coin divided by the ampere square. So it's going to give us a kilogram meters per second squared times amperes to the negative 2. So then we also get that the unit of R for B is the meters, and the unit of I is the amperes. Hence, the unit of B will be the unit of mu naught times the units. We have the unit of mu naught times the unit of current divided by the unit of meters. So this will definitely give us the base unit of B will be the base unit of mu naught, which is, here is it, and the base unit of I, which is the ampere, and the base unit of R, which is the meter. Now 2 pi is a dimensionless constant, so it's going to take a unit 1, and so simplifying, we get that the base unit of B will be the kilogram per second squared per ampere. Now we proceed to get the base unit of BIL, that's the right hand side, and since the base unit of B is this kilogram per second squared per ampere, we multiply the unit by the unit of the current A, so that's the current, and here is the length M. And so getting that, we realize that the unit of BIL is the kilogram meters per second squared, which is similar to what we had above as the unit of F. And so what then do we conclude? We can conclude that since the unit of the right hand side is equal to the unit of the left hand side of the equation, then the equation is homogeneous as required. And that is all about question 1. Let's move to the next question. Okay, question number 2. It reads, a metal wire is illuminated by a light of wavelength 3.5 times 10 to the negative 5 centimeters. A metal has a work function of 2.5 electron volts and a threshold frequency of 497 nanometers. A threshold wavelength of 497 nanometers. A. Define the underlying phrases, that is, the work function and the threshold wavelength. B. Calculate the maximum kinetic energy of the emitted photoelectrons. And C. Determine the stopping potential of the metal. So we start by defining the underlying phrases. So the first is, we have the work function. So the work function is the minimum amount of energy required to induce photo emission of electrons from a metal surface, and the value depends on the metal. If you have any difficulty, I'm going to drop the link to photoelectric effects on this same channel, which you can view to enlighten your understanding on this particular topic. Now we have the next, which is the threshold wavelength. The threshold wavelength is the maximum wavelength that is required for the radiation such that photoelectrons should be emitted from the surface of the metal. In very brief terms. Okay, so let's go to the next question, which says we should calculate the maximum kinetic energy of emitted photoelectrons. So the procedure of photoelectricity and how it occurs was explained in one of my videos, and the link will be dropped in the comment section, so you can just click and get an understanding of the lesson as a whole. So to calculate the maximum kinetic energy of the photoelectrons, we are going to use the kinetic energy will be equal to HF minus HF naught, where HF is the energy of the incident radiation and HF naught will be the work function, that's W naught. But since we were given the wavelength was 497 nanometers. So this is a threshold wavelength. The wavelength of the incident radiation was 3.5 times 10 to the negative 5 centimeters. Then we can change the frequency to C on lambda, since we know that speed is equal to F lambda. So from there we can get lambda to be equal to F to be equal to C on lambda. And so when I replace, we get HC on lambda minus W0, where W0 is the work function of the metal. Okay, so let's do some numerical application, and we get that the maximum kinetic energy is equal to Now, 6.62 times 10 to the negative 34, that's the value of the Planck's constant, times c, which is the speed of light, that's 3 times 10 to the power 8, divided by the wavelength, which is 3.5 times 10 to the negative 7. So I converted from centimeters to meters, that is, from this and multiply by 10 to the negative 2, and from indices, if I sum these two, it gives 10 to the negative 7. And then since my work function was given in electron volts, that is, the work function was 2.5 electron volts, then I just had to convert this particular answer in electron volts, and that is done by dividing the answer by 1.6 times 10 to the negative 19 joules. So having this, I can now get my answer exactly in electron volts. If I cancel this, it means that my answer will be in joules, and to convert from joules to electron volts, we divide by 1.6 times 10 to the negative 19, and the reverse is true, that is, to convert from electron volts to joules, we multiply by 1.6 times 10 to the negative 19 joules. So this will be minus the work function, which is 2.5, and then numerical application gives 3.55 as the maximum kinetic energy. Now the C question says we should determine the stopping potential. Now from the video, which the description is in the link, we are going to see that the maximum kinetic energy is equivalent to EVS, where Vs is the stopping potential. And so from there we can draw the stopping potential to be the maximum kinetic energy divided by electronic charge E. And so we get that from numerical application, we get that Vs will be 3.55 electron volts divided by E. So you see that the electronic charge E, we simplify with E, and our final result will be 3.55 volts. So that is the stopping potential. So let's proceed to the next question. So let's get to the next question. In an experiment to demonstrate Rutherford scattering, alpha particles are fired in a gold foil. One alpha particle is fired directly so that it comes to full stop at 2.08 times 10 to the negative 12 meters from the nucleus, before being deflected backwards along its initial path full stop. An alpha particle carries a charge of plus 2e, where E is the electronic charge, with a mass of 6.64 times 10 to the negative 27 kilogram, and a gold nucleus carries a charge of plus 79e. State any two conclusions from the Rutherford alpha particle scattering experiment with the gold foil. B. Assuming the alpha particle started with zero electric potential, find the electric potential difference between the starting position and where it stopped. C. Calculate the speed at which the alpha particle is fired. Now, state any two conclusions from Rutherford's alpha particle scattering experiment with gold foil. So here I gave three. So the first is, what did Rutherford observe? He saw that most of the space inside the atom is empty because of the alpha particles who pass through the gold foil without getting deflected. So it means an atom is mostly made up of empty space. Now the next, very few particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. The next observation, so you can choose any of these two. A very small fraction of alpha particles were deflected by very large angles, indicating that all positive charge and mass is of the gold atom, from the gold atom, were concentrated in a very small volume within the atom. So those are the observations that were made, and these are the conclusions that were drawn by Rutherford for this experiment. So let's go to the B part and let's see a picture of the problem. Okay, so let's get a picture of the problem. Assuming the alpha particle started with zero electric potential, find the electric potential difference between the starting position and where it stopped. So here we have our alpha particles which moved and collide or went closer to the gold foil nucleus, and the gold foil has a charge of plus 79 E, and so the distance between the two was given to be 2.08 times 10 to the negative 12 meters. And so now we are about to calculate the potential difference, and the PD is going to be the potential at B minus the potential at A. So we are going to call the 2 points here, we'll call this point B and we'll call this point A. But they said the potential at A is 0, and so how do we get the potential at B? From VB, that's the potential at B is KQ divided by the separation, that's the distance D. It means that we can simply do numerical application where K is a constant, which is 9 times 10 to the power 9 SI units. Now in electrostatics, we see that K has a value, or we see that K is equal to 1 divided by 4 pi epsilon 0. So an application of this value gives approximately 9 times 10 raised to the power 9 SI units. Okay, so from there we can calculate the potential at B, which is KQ divided by the distance D. And so we have 9 times 10 to the 9 times, there we have 2 electrons, so the charge of the alpha particle is 2e, so it will be 2 times 1.6 times 10 to the negative 19 divided by the separation, which is 2.08 times 10 to the negative 12 meters. And so numerical application gives us 1384.62 volts, and then the potential difference will now be VB minus VA, which will give us 1384.61 volts. Now we go to the next question. C says calculate the speed at which the alpha particles move or is fired. When the alpha particle was fired, it was fired and the alpha particle had kinetic energy. But immediately when the repulsive force between the gold nucleus and the alpha particle was strong enough, it brought him to momentary rest, and so his final kinetic energy became 0. And at that stage, he gained electric potential energy. And so to conserve energy, it means that the electric potential energy in the beginning plus the kinetic energy of the alpha particle in the beginning, that's initial, should be equal to the electric potential energy final plus the kinetic energy final. But the final kinetic energy is 0 since the alpha particles was brought to rest. This is here starting position and where it stopped. So stopping means he has no speed, and no speed implies no kinetic energy, and so he has an electric potential energy. Whereas in the beginning the potential was 0, and hence if the potential is 0, there is no potential electric potential energy, so this will be 0. And so we see that the initial kinetic energy will be equal to the final electric potential energy, and on that base we can calculate the speed with which the alpha particle was fired, knowing that the kinetic energy is given by a half mv squared. So let's get the value. So we get that the kinetic energy is equal to EPE final, which implies that a half mv squared is equal to KQ1 Q2 divided by D, where KQ1 Q2 divided by D is the electric potential energy. And so we make V the subject of the formula, and from there we see that V will be equal to the square root of 2k Q1 Q2 divided by D divided by MD. Okay, so from there we do numerical application, so we are going to substitute the values given. So we have that we have 2 times k, which is 9 times 10 raised to the power 9, and we have times q1, which is 2 times 1.6 times 10 to the negative 19. q1 is my plus 2 charge, plus 2e charge, and q2 will be my plus 79e charge, which is 79 times the electronic charge e, which is 1.6 times 10 to the negative 19 coulomb. All of that divided by the mass. So the mass of the alpha particle is 6.64 times 10 to the negative 27, which was given in the question, times the separation where it was brought to momentary rest, so it is 2.08 times 10 to the negative 12. And so doing this numerical application, we get approximately 2.3 times 10 to the power 6 meters per second. Now, question number 4. An object is placed 12.0 centimeters in front of a converging lens of focal length 10 centimeters. A diverging lens of focal length 8 centimeters is placed 22.0 centimeters from the converging lens as shown in the figure. So the figure was not drawn, so we are going to have an analysis of the figure. Now the question was calculate the distance of the final image from the diverging lens. So I have a convex lens or converging lens. So here is my lens, and somewhere I have diverging lens, something of this nature. Forgive my diagram. Now let's see that's my optical center, that's my optical axis. Now our object can be found here. Let's call that, let's call it there, or let me place it a little bit behind. So I'll place it here. That's our object. Okay, now we observe that we have a two-way system, and so we have to draw the Ray diagram which actually represents this scenario. So how then do we do to know the characteristics of the image that we are going to have, and where exactly are we going to see this image, and how is it going to look like? So it is more preferable to get your calculations before you draw, because it takes a lot of experience on lenses to just get the scenario locked. So I'm going to pass through the methodology where we are going to leave from the calculations that we have in order for us to complete this ray diagram, so that we can see the exact position where this image is going to be formed. Now the focal length of our converging lens is 10 centimeters, and I'm going to call this a positive lens and I'll call this a negative lens. Why? Because the focal length of a converging lens is positive, and that of a diverging lens is negative. So put that in mind. Now we have to calculate um, the object distance, sorry, the image distance, number one, when we are dealing with the convex lens. So here is our focal point F, and here from the center of the lens right up to this point, it was given to be 12 centimeters. So that is our U. Our U is 12 centimeters, and the focal length is 10 centimeters. So I'll put a plus in front so that we should know that the focal length is positive. So from here, we can now use the lens formula to have the image distance, and note that the distance separating the two lenses was given. So the diverging lens of focal length 8 is placed 22 centimeters from the converging lens. So this distance is 22 centimeters. So then calculate now we can calculate the image distance in the convex lens configuration. So using the lens formula, we have 1 over f, I will call it f1, or f concave, will be equal to 1 all over u, I'll call it u concave, plus 1 all over v concave. So it means it is formed like this with respect to the convex to the converging lens. So it means here we are looking for VC. So if you make VC the subject, VC will simply be UC FC divided by UC minus FC. So this means that my VC will be equal to, we have UC. Our UC is 12 times 10, which is the focal length, divided by 12 minus 10. So 12 times 10 is 120. 120 divided by 2, which will give me 60 centimeters. And so from here, it means that the object which I'm going to observe is going to be somewhere here on this side. And how is it going to be? So there we have to check the magnification. So what's the magnification of the lens? The magnification of the object is simply given by negative v divided by u. So this will be equal to our v is 60. So our negative 60 divided by um, our object distance, which is 12, and 60 on 12 give us 5. So that will be negative 5. Now the negative 5 means that the image is going to be inverted. So it means that our ray will pass somehow and it's going to be deviated and reach somewhere. So you can pass another ray. You don't necessarily need many rays. You can pass another ray through the center, in which this will definitely deviate it. So it means our object is going to be found somewhere here. Let me replace this. Forgive the straightness of my line. Okay, so let's just hold this as the object. So this is the distance from here to the center of our lens is 60 centimeters, and so we will have to get exactly there, because this is the first configuration gives us the object distance very far at this extent, and so it means that we have to get the final image, because what we are looking for is calculating the final image from the diverging lens. So it means this is not the image, the final image from the diverging lens. Now this 60 centimeters will now become our object distance with respect to the diverging lens, and we already see that our object is inverted. So if it is inverted, we definitely have to get an image with respect to this lens. And so definitely, since it is inverted, it means that this object distance u, call it u divergent, it will definitely be negative 60, because it is in the reversed sense, so it is negative. So from there, we will now calculate the new object distance. Now, what would our object distance be? Remember that the focal length of a diverging lens is negative. They will not give you as a negative value, but you have to note that. So from here, we get that from the lens formula, 1 on f is equal to 1 over v. I will use a little bit up. So let me clean this. Okay, so we have 1 over f is equal to 1 over u plus 1 over v. So call that v divergent, divergent, divergent. So what does it imply? So this means that our vd will be equal to, similarly, so it's going to be ud fd divided by ud minus ft. Now, what is our image? What is going to be our object distance? So we saw that the object distance with respect to the diverging lens configuration will simply be negative 60. So we have ud is equal to negative 60 centimeters, because the object is inverted, and our focal length fd, the focal length of the diverging lens, is 8.0 centimeters. So it's going to be negative 8.0 centimeters. So this means our image vd will be equal to udft, so that's negative 60 times negative 8, all of this divided by ud. Our ud will be negative 60 minus 120. So negative 60 minus the focal length, that will be negative 8. So we do the calculations on numerical applications. We give we have 60 times 8 divided by okay. So we have our v, we have our VD to be approximately negative 9.23 centimeters. So it means that our object or our image will be formed. Now, since the image will be formed somewhere there, we can now get the magnification M. Now, the magnification will simply be negative V divided by U, which is it will give us positive 9.23 divided by negative 60. That will be this divided by 60. So it's going to give us negative 0.15, approximately negative 0.15 approximately. So that's the magnification for the diverging lens. So what we get is we see that the magnification is still negative, and so we are going to observe the image is actually diminished since the magnification is less than 1. So we can have something like this that we bend. I will have another one which passes through the center. I'm going to maintain the same, and so our image will be somewhere here. Yes, we are not scale. So this distance is distance from here to here is the negative 9.23 centimeters. Okay, now if we want to get the final magnification of our image, the total magnification of the image, M total, is simply going to be the product of those two magnifications, M1 times M2, which is negative 0.15 times the magnification of the first was negative 5. And so we get about positive 0.76. So it tells us clearly that that image is diminished, and so that brings us to the end of this video. So the final distance we're calculating concerning the lens is this here. So it's VD. So that's where the question normally ends, since we have calculated VD. So this was just to check the orientation of the object. So that is the ray diagram, and thank you very much for watching this video. Please do not forget to like, share and subscribe. See you in the second part of the Northwest Regional Mock. For the sake of longevity of videos, so I decided to split it into parts. Now in the next part we continue with question 5, where we have a potentiometer problem to solve, and then we proceed with one of those options and data analysis. So see you in the next video. Thanks for liking, thanks for sharing, and thanks for subscribing. Stay blessed.